Hey everyone, welcome back to physics. This is going to be lecture 14 of the course. And in this section, we're going to continue with our discussion of Newton's laws of motion and take a closer look at Newton's second law. So let's go ahead and jump into it. And we'll call this section 3.3, Newton's second law. Okay, so let's go ahead and restate the law. We mentioned it earlier in a previous lecture, but let's go ahead and restate it. What do we say here? We say that forces accelerate objects according to, and it's the sum of the forces involved is equal to the mass times the acceleration. So that's our very concise statement of Newton's second law. So it really is a law that relates forces to acceleration. All right, Newton's first law, with Newton's first law, we saw that when a body is acted upon by a net force equal to 0, that body's velocity is constant, right? But what happens when the force is not net zero? Right? So what happens when the force is not net zero? That is the domain of Newton's second law. Okay, so let's think this through. And I think a lot of this is going to be relatively intuitive, but let's just, for the sake of completeness, let's go ahead and talk through this thing. So let's imagine we have an object moving on we'll just think of it as a frictionless surface. Okay, so I've got some mass here. This is the same object at 4 different times, moving on a frictionless surface, right? And so we know that if the net forces is equal to 0, then the velocity will be constant, right? So if the net force is 0, right, i.e. the sum of the forces equals 0. So if the net force is 0, then the velocity is constant, right? And so that's what we see here. So time 1, time 2, time 3, time 4, the velocity is constant. There's no net forces at work on this mass. Right, now let's consider the same object on a frictionless surface, this time moving under some non-zero net force. Right, so let's say that there's some constant force being applied through all of these different time periods, and we'll say that it's kind of a force off to the right here. Okay, so what we'll say here is when the net force, the sum of the forces, is greater than 0, and what I mean by that is you can coordinatize these things in different ways, but the way I'm coordinatizing it is when I say that the net force is greater than 0, what I mean by that in this instance is that the net force is in the direction of the velocity. So i.e. the net force is in the direction of the velocity. Okay. So when the net force is greater than 0, i.e. in the direction of the velocity, then the acceleration vector would be greater than 0, magnitude of the vector would be greater than 0, and we will see the velocity increase. Right, so I've got this object, I'm applying a force, a constant force, we'll say, to the right. And so that's going to result in some acceleration, a non-zero acceleration vector in the same direction as the force. Right, and so what that'll translate into is an increase in velocity, right? That's an acceleration. And that's what happens when we have a net force that's not a non-zero net force, right? So the force is to the right, creating an acceleration to the right, which obviously is going to increase the velocity of the object. And similarly, if the net force is in the other direction, right? If I've got a net force in the other direction, right? So let's say my force is this direction, okay, right? So if the sum of the forces is less than 0, i.e. in the direction opposite the velocity, what's going to happen to the velocity? Well, the acceleration will be in that same direction, and the velocity will decrease. Right? So you imagine if I have a net force pushing off to the left, then I'm going to have an acceleration vector in that direction, aren't I? Right? And so if my velocity starts out like this, then it's going to slow down. Right? So my velocity would decrease and eventually stop and turn about. Right? Right? So long story short, the presence of a net force on a body causes the body to accelerate in the direction of the net force. Right? So that's kind of the long story short, right? The presence of a net force on a body causes the body to accelerate in the direction of the net force. Okay, and so that's what is happening here. Okay, so clearly when the forces all equal out, the velocity is constant, as we saw with the first law. Now when the net force is non-zero, then you're going to have some kind of an acceleration in the direction of the net force. Okay, and then we see the impact that has on the velocity, depending on whether or not the force is in the direction of velocity or against the direction of velocity. Okay, now there's this equation, F equals ma. There's a number of things to think about. Like, this is more complex than just a simple F equals ma, right? So there's a couple of different ways to think about it. So one of the things to think about is the fact that it turns out that the magnitude of the acceleration is actually proportional to the magnitude of the net force. So the magnitude of the acceleration is directly proportional to the magnitude of the net force. Right, this is just how the world works. This is kind of remarkable, actually. So we say that and you can see this in the equation, the magnitude of the acceleration is equal to the magnitude of the net force divided by the mass, which you can kind of think of the mass being the dividing by the mass as really just the reciprocal of the mass. Right? So the reciprocal of an object's mass, that quantity, is the constant of proportionality between acceleration and force. Okay, so that's kind of an interesting thing. This is the constant of proportionality. For an object. Okay, so that's kind of interesting, right? Another way to think about this equation is to say that the ratio of the magnitude of the net force and the magnitude of the acceleration is a constant, right? Another way to think about it is to say that the magnitude of the net force, the ratio of the magnitude, the ratio of the magnitude of the net force to the magnitude of the acceleration is constant for a body, right? Irregardless of what the force is, it's constant. What do we mean by that? Well, remember, we're starting with F equals ma, right? If I solve for m, I've got the magnitude of the sum of the forces divided by the magnitude of the acceleration. That's equal to the mass. Okay. Right, and I mean, I think what's really nice about this is really a different characterization of mass than we're used to, right? Now, so if you've been kind of following these lectures, I have been alluding to this, I have alluded to this repeatedly, but the mass of the body, the mass of a body really describes what we call the body's inertia. The larger the mass, the more the body will resist acceleration, right? And so that's the kind of thing we're seeing up here. Acceleration is 1 over m times the net force, right? And so the larger the body, it's going to require more of a force to accelerate it, right? And you can see that in this characterization, and then this characterization here really shows you that the ratio of these two, of the magnitude of the net force and the magnitude of the acceleration, is equal to this constant, which is m. Okay, and this is very this is very intuitive, actually. If you think about how you experience the world, let's do a little experiment in our minds here. Let's think about a baseball and a bowling ball, right? So let's say I've got two balls. One is a baseball, right, with a mass of, we'll say in this case 0.145 kilograms. And then I've also got a bowling ball, which is a larger ball and a more massive ball. Right, and the mass here is 6.5 kilograms. Right, now it would be possible to set up some kind of an apparatus whereby I apply a force, an equal force, to each of these balls, right? And so maybe I consider the force here to be 10 newtons, and I want to have the same force here, right? And so, I mean, we can use F equals ma to back out whatever acceleration we would get from applying a net force of 10 newtons to each of these. And so on this side, we would say 10 newtons divided by the mass, 0.145 kilograms, means that I'm going to see an acceleration of approximately 68.97 meters per second squared. Right, so that's the acceleration of the baseball using this force. Now over here, same force, different mass, so 6.5 kilograms. And obviously when I do that division, I see that the acceleration I'm going to get over here is quite a bit smaller, 1.5 meters per second squared. Right, and so given the same force, the acceleration on the baseball is significantly larger, right? Because the bowling ball is more massive, it has more resistance to being accelerated, it has more inertia. Okay. All right, very good. So there's a deep connection between force, mass, and acceleration, and this equation really kind of encapsulates a lot of it. Okay, so let's look closer at this F equals ma and kind of dig into some of the characteristics of it. And then we'll do some examples of see how we can use this. So the first thing to note here is that this equation is a vector equation. Right? The only time you can think of it as a non-vector equation is in the case of 1D. But in 2D and 3D, certainly we have to think of this as a vector equation. Okay, and so this is we've been using kind of a shorthand notation up to this point, but let's think about what this equation really means in three-dimensional space. Right, so what we're really talking about, and there's different ways to notate vectors. One way to notate them is to use kind of a component notation like this. So you've got the x component of the net force, you've got the y component of the net force, and you've got the z component of the net force, right? And so that vector is equal to the mass times another vector, which is the acceleration vector, x component, y component, z component. That would be one way to write F equals ma in a three-dimensional context. Right, another way, if you like the ijk notation more, you could write f sub x I hat plus f sub y j hat plus f sub z k hat would be equal to the mass times a sub x I hat plus a sub y j hat plus a sub z k hat. All right, so you can write it like that. Right, but very often when we're solving problems using f equals ma, we'll want to think of the components separately. It's very often the case that it's advantageous and simplifying to think of these three components separately. So you'll have like the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. The sum of the forces in the y direction will be equal to the mass times the acceleration in the y direction, and the sum of the forces in the z direction will be equal to the mass times the acceleration in the z direction. And so very often you can think of it in the context of the three separated out, right? But sometimes you can't, and that in those cases these other notations are super helpful. Another thing that to point out is let's think about this sum of forces. Right? Let's think about this piece here. Right? This sum of the forces, right? I.e. the net force. It can be shown experimentally that if we were to apply a range of forces, let's say we have, so it can be shown experimentally that applying like f1, f2, dot, 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 f of n to a body produces the identical acceleration as the single force, as applying the single force, right? And the single force being the sum of all. Remember, these are just vectors, right? If it's a two-dimensional space, these are 2D vectors. You just add them all together. So if I were to add all of these together into a single vector, I would get just this guy here. And, you know, if I have a body and I apply, you know, F1 and I apply F2 and I apply F3 and maybe I apply F4, we'll just go with that for now. You get the same acceleration as applying F equal to F1 plus F2 plus F3 plus F4. So you get the same acceleration as if I did just F to this thing. Okay, and so that's kind of the key. I mean, Newton was very, very clever to recognize this fact that it doesn't matter if I apply all the forces separately or if I figure out what the net force is and apply it individually. I get the same acceleration. I get the same motion out of the body. Right? And so this can be demonstrated experimentally. If you were to take a physics course, this would probably be one of the experiments you would do. You would try applying a bunch of forces separately to a body. You'd note its acceleration, its motion, and then you would sum all those forces and apply that single force, that net force, to the body. And you would note that the same motion occurred. Right? And so this is really what is being accomplished by the left-hand side of Newton's equation when he says the sum of the forces. Right, so this piece here is really just this fact that I can apply a bunch of forces individually, or I can sum them all up and apply them as one net force, and I get the same acceleration. Okay. Let's see. Another thing to think about when thinking about F equals ma is to notice that when we say F, the forces here, I don't know if, well, we didn't say it in our statement of the principle, but in general, we're only talking about external forces. So when we say the sum of F, we are only concerned with external forces. Meaning, you know, a push or a pull from some other cause, right? So we can't, for example, I mean, we kind of assume as an axiom that a body cannot be moved by an internal force, right? A body can't be moved by an internal force alone, right? Right. So certainly I can use the muscles that are internal to my body, but I have to exert those muscles on either the ground or on something that I pull myself against, whatever. So there's an external force at work in any kind of motion, right? And that's really what you have to consider when you're kind of using this expression. And then I guess the one other thing to note is that m in the expression is assumed to be constant, meaning it's not going to change. Like within the context of a single problem, you wouldn't want your mass to be like a fluctuating quantity, right? So you can think like if you were trying to solve a problem using F equals ma and involving like a tanker truck, and that tanker truck was leaking water, right, over some interval of time, then clearly the mass of the system is going to be changing, right? And in those circumstances, you would have to consider that's a special. You'd have to engage in sort of some special considerations of that kind of system where the mass is fluctuating or changing, right? So for the problems we'll be working on, we're just going to assume a constant mass. But I mean, there are ways to deal with that sort of thing, obviously, but we won't be kind of concerned with that at first. All right, let's do an example. We'll do two examples here, just to get used to the idea of how, or just to kind of see how this can be used. Okay, so the first example goes like this. So let's say, these are both kind of simple examples. I really just want to get the idea of how we can use this out. So a 5 kilogram block is placed on a frictionless surface. Okay, a constant force of 20 newtons is applied to the block. Okay, all right, so we've got just this block sitting on a frictionless surface, and we're going to push it with a force of 20 newtons. All right, let's say we want to calculate the acceleration and also the displacement, and we'll say after 4 seconds. Okay, so simple setup. We've just got this block sitting on a table or something, and it's a 5 kilogram block. And then we come along and either push it or pull it, but either way we exert a force of 20 newtons on this thing. Right, so like this. And so then the question is, what's the acceleration, and also what happens to the position of this thing after 4 seconds. Okay, so notice this is a one-dimensional problem, right? This is a 1D problem, and it's a 1D problem because even though we're not told what direction the force is, it's just one force at work, and it's constant, meaning it doesn't change directions. It's just constant in a certain direction, a certain magnitude. And so we can model this in 1D. Right, and so we can use F equals ma to identify the acceleration. Right, and because it's 1D, we don't even have to think about this as a vector. We can think about it just as numbers, as the magnitude is going to be the same as the vector value, right? The vector component. And so we could say, to find the acceleration, it's just going to be A is equal to the sum of the forces divided by the mass. In this case, the sum of the forces is 20 newtons, and the mass is 5 kilograms. And so that means the acceleration is 4 meters per second squared in whatever direction the force is being applied. Okay, so the acceleration of the object is 4 meters per second squared. All right, so once we know that, we can just use basic kinematics to identify the displacement, right? And so the kinematics equation we could use is just imagine this thing moving along the x-axis. We could say the final position is equal to the initial position plus the initial velocity times the time plus 1/2 times the acceleration times t squared. right? And so in this case, this is 0, that's 0. I mean, at least that's how we should interpret the problem. We assume that it's just placed there, right? And it's 0 initially, right? And so we can just plug in the acceleration, which we just calculated as 4 meters per second squared. And we're going to apply that force for 4 seconds. And so that acceleration would be 4 seconds, would be constant for 4 seconds. All right, so we get this thing here. And then, of course, when we do all that math, you'll see that this turns out to be 32 meters. All right, so given the force of 20 newtons, the object will be displaced 32 meters after a 4-second interval. All right, so if you apply that force constantly for 4 seconds, that is what you should expect. Okay. So that's the first example. Again, just very simple, just showing how you can use F equals ma to bridge the gap between given a force to what is the resulting acceleration the body undergoes, and then you can just plug those quantities into a kinematics expression. Okay. Let's do another example, similar, but let's move into 2 dimensions here and think about how this would work. So let's say I've got a 3 kilogram block is subjected to 2 forces, okay, in the plane. All right, so I got 2 forces in the plane. The first one has a magnitude, we'll call it F1. It has a magnitude of 12 newtons. And in the positive x direction, okay, and the second one has, we'll call it F2. It has a magnitude of 5 newtons in the positive y direction. Okay, and what we want to do is we want to know, like, we want to calculate the object's acceleration. Calculate the object's acceleration and its displacement after, we'll say, 3 seconds. Okay. All right, now don't worry. I know that, so these are kind of simple problems, right? So if you're using this as a supplement to some course, you're going to be like, these are too simple. Don't worry, we'll do more complex examples later. We just want to start with the basic kinds of questions that this second law of Newton can help us answer. We're starting with the basics, and we will come up with tricky, crazy physics problems in a later section. We want to start simple, right? So the basic setup is I've got this block here. It's 3 kilograms, and it's in the plane, and there's a force being applied in this direction, which is has a magnitude of 12 newtons. And there's a force being applied in this direction, which has a magnitude of 5 newtons. Okay, so 2 separate forces operating on the object in a in different directions, actually directions that are perpendicular to one another. Right, so we obviously can guess that the object is going to move kind of more like this, isn't it? It's going to kind of have a diagonal trajectory. It's not going to go in the x direction or the y direction. It'll go kind of in both, right? And so our ask is to figure out what is the acceleration of this object, and meaning, you know, both the magnitude and the direction, and let's get the vector as well. And then where does this thing end up 3 seconds after the forces are applied? Okay. So again, we can think of the object as being situated at the origin, right? And the 2 forces are perpendicular. So this is like the x-axis here, and this is like the y-axis. Okay, so obviously it can become more complex, you know, when we start to deal with forces that are not perpendicular like this. But we'll start with this one. Okay, and because the forces are perpendicular, their magnitudes are face value, right? So the x component of the force is equal to 12 newtons. The y component of the force is equal to 5 newtons, right? And from this, we can calculate the x and y components of acceleration. So the x component of acceleration is going to be equal to the force divided by the mass. And so it's going to be 12 newtons over 3 kilograms, which is 4 meters per second squared. And the y component of acceleration will be equal to the force, the y component of the force divided by the mass. So it'll be 5 newtons over 3 kilograms. And so we get 1.67 meters per second squared. Okay, and so the acceleration vector is this guy. It's going to be equal to 4 meters per second squared I hat plus 1.67 meters per second squared j hat. Okay, so that's the acceleration vector. And so from this we can derive both the magnitude of the acceleration and the direction. And so the magnitude of the acceleration is going to be equal to 4 squared plus 1.67 squared. Take the square root of that, just the magnitude of that vector. And you'll see that you get, what, 16 plus 2.79, square root of that. And you get about 4.33 meters per second squared. That's the magnitude. That's purely the magnitude of the acceleration. What's the direction of the acceleration? Well, you can think about this, just a little bit of trigonometry, right? So you've got a theta here, and then you've got your a sub x, your a sub y, and then your acceleration. And just plugging in those values, this is a 4, this is 1.67, right? So we want to know that direction. You can just use the tangent of theta, which would be a sub y over a sub x. And of course, theta would then be the inverse tangent of that. And a sub y is 1.67, and a sub x is 4. And so therefore, theta is equal to about 22.5 degrees or so. Okay, so kind of going back to our original, this is going to be about 22.5 degrees. And the magnitude here is going to be about 4.33 meters per second squared. So that's the rate, 4.33 meters per second squared, the rate of the change of velocity by time, and then the direction off of the horizontal is about 22.5 degrees. Okay. And so then the next question is, what's the displacement after 3 seconds? What's the displacement after 3 seconds? Well, again, we can just use the kinematics expression. So we'll start with the x coordinates. So x sub x final is equal to x initial plus v initial x times t plus 1/2 a sub x t squared. Okay, and so the initial position we'll say is the origin, so the x component is 0. So that's a 0. And the initial velocity, we'll say it's at rest, so that's 0. So really all you need is this thing. And so it's 1/2, and then the acceleration in the x direction we saw is 4 meters per second squared, and that's going to be for 3 seconds squared. And so altogether, when you do that math, you get basically 2 times 9, so 18 meters. So this thing moves 18 meters in the x direction, and then for the y component, you get 0 and 0 here again, so it just jumps straight to this. It'd be 1/2 a sub y t squared. And so 1/2, and the acceleration in the y direction we calculated up here as 1.67 meters per second squared. And then we're going to apply that acceleration for 3 seconds. And when you do that calculation, you'll see that you get about 7.52 meters. Right? And so what that means is the object starts at the origin, and then it moves up some way up here, and really what it's doing is it's going, about 18 meters in this direction, about 7.5 meters in this direction, right? So really what we want to know is, like, what is the length, what is the distance altogether here, right? And so, of course, the distance there is just the displacement, right? You can just use the distance formula. So the square root of 18 meters minus 0 meters squared, so that's just 18 meters squared, plus the displacement in the y direction starts at the origin, so 7.52 meters minus 0 meters, so 7.52 meters squared. And then when you calculate all of that, you'll see that this thing moved about 19.5 meters. And we know the angle is 22.5 degrees. Okay, so we now know what the acceleration vector looks like. We know exactly what angle it's moving off, and now we can see exactly how far it went. Right, and so the key here is the key point here is to note that we started with just two forces, and then because these two forces are operating in the x and y direction separately, we can calculate their acceleration in those two directions using Newton's second law, F equals ma. And then from that, it's just a kinematics problem once you have those acceleration quantities. Okay, very good. So we'll leave it there. And again, we'll come back and we'll do more challenging problem types later, but this is just an introduction to Newton's second law. And so in the next lecture, we'll get into Newton's third law, and then after that, we'll start digging into some more concrete applications of these three laws, because there are very novel and very interesting physics problems that can be solved just using these three laws of Newton, and alongside the kinematics equations that we've used up to this point as well. All right, so we'll leave it there, and we will talk to you all next time. Take care.